this second week entitled The Art of Computing, okay? It will be, for some of you maybe easy, for some of you not, but it is basically the basic mathematics that we use in the weeks that will come next, okay? But don't be afraid, it's very easy. For example, do you get intimidated the moment you see an equation? Do you? No. Do you know analytic function? Have you heard of it before? Okay, you need to interact with me, otherwise I can just come here and speak to myself. Have you heard of it? What is an analytic function? Most of the functions that we use are analytic functions. And this time I wasn't that lazy. I actually cropped some information from Wikipedia and put it in the slides. So analytic function is basically a function that can be written in this form, right? Basically a0 plus a1, x minus x0 plus a2, x minus x0 squared, etc., right? And most of the functions, well-behaving functions, are analytic functions. Like, for example, polynomials, right? Exponential function, trigonometric function, logarithm, power functions, okay? And when you are doing this around x0 equals 0, you get yourself Maclaurin series. Any other place, including 0, you call them Taylor series. Let's look at Taylor series. Before we go, there are functions that are not analytic. And I didn't put them here. For example, an absolute value function is not analytic. Do you know how it looks like, absolute value? Yes. Okay. Okay, coming to Taylor series. Actually, Taylor series are really connected to analytic functions. Meaning that every function, every analytic function, infinitely differentiable, can be written in this form. Okay? Let's, for example, do it for typical functions that we know. For example, an exponential function. Okay? Let's open this, and I will open it. Okay. So, for example, e to the x. Let's find how it can be written in the form a0 plus a1 x minus 0 plus a2 x minus 0 squared, etc. Right? What are a1, a0, and a2? So let's let's remember the definition. Help me out with this. What was the definition? The sum from n equals 0 to infinity, the nth derivative of fx, right? Divided by n factorial times x minus x0 squared. And this is x0. Do you agree? Everybody agrees? This one? Which one? Ah, sorry. Let's erase this. Okay. So what is the derivative of if fx is, so we are doing it around x0 equals 0, okay? Which means we are doing Maclaurin series. So if fx is e to the x, what is the first derivative of fx? E to the x, right? That's why e to the x keeps coming out in, will keep coming out in all the equations because its derivative is itself, right? Uh, let's think about what it means first, okay, for a while. What it means to have derivative that is equal to itself. For example, if you have something like 1, 2, 3, 4, 5, 6, 7, blah, blah, blah. Then if you write down the differences, it's constant, right? I know it's a childish way of thinking about things, but still, bear with me for one more moment. So what about the squares? 1, 2, then 1, 4, excuse me, 9, 16, 25. What is the differences? What are the differences? 7, 9. Right? And the differences of the differences gets boring immediately, right? What if you have 1, 2, 4, 8, 16, which is closely related to e to the x, right? It's e to the ln 2 times x, right? So what is the difference? 1, 2, 4, 8, 16. What is the difference? 1, 2, 4. Have you done it before? No, right? It's fun to do it at least once in your lifetime. So this is this is why exponential functions keep coming out, because their difference is themselves, right? So let's go back and put down the equation here. So e to the x is basically starting with a0, right? Which is 1. So we need to start with f of x, right? At x equals x0, which is 0. Anyways, we need to find e to the 0, which is 1, right? Then what is the next term? It's the derivative of fx at x equals 0, right? What's the derivative of fx? E to the x, and e to the 0 again 1, right? But remember, we had divided by n factorial, so we have 1 divided by 1 factorial times x. Do you agree? The next term is the second derivative of e to the x, right? And again, it's e to the x, so e to the 0, it's 1. Am I going too slow? Yes, I'm going, no? Okay, 1 over 2 factorial x squared, and etc., right? Okay, let's actually plot these things. Okay, I made some plots. Do you want me to start from scratch or to use the code that I wrote already? Which one do you prefer? From scratch? From the start. Okay, clear. Okay, let's call this computing version 1. Okay, so I will define x to be between -3 and 3. First of all, do you understand what this means? It means that I will go from -3 to 3 with these steps. Okay, let's run it, and you will see that you have x has 600 points. Let's start with -3, then the next one is -299, to -298, etc. Right? So since we haven't done it before, let's plot a function. Okay, plot x versus exponential of x. Okay, and when you run it, you get the function. Okay, any questions so far? No? So what I want to do now, I want to see if this is indeed true or not. Okay, I will add these polynomials and see whether it approaches to e to the x or not. Are you with me? Have you done it before? No. So let's define something like total. Okay, this will be our total function. So let it has at the beginning the same size as x does. So as we go along, we will learn a lot of MATLAB tricks. So one of them is, for example, the size of x. This will return you the size of x vector. Okay, right? 1 times 601. Okay. Now that we run the whole thing, total is now a vector that has only zeros, but it has the same length as x does, right? Now I will start adding functions. Let's say for n equals 0 to 5, I'm taking first 6 elements of this series, okay? Let total be equal to x dot to the n. Why did I put dot here? Do you remember from the previous hour? Element-wise, I'm taking the power of x element-wise. I'm taking the power of each element. Divided by, let's close this. Divided by factorial of n. That's how you get factorial. Factorial 1. Didn't work. What about this? Will it work? Yay. Do you know what it is? Okay, I should not do it right now. Let's continue. So I want to add total plus x to the n divided by factorial n. Do you think it's okay so far? Yes? So let's actually, we didn't like the way it looked, right? It should be like the line width should be bigger, maybe 2, maybe 3, okay? So what I'm going to do is, if I run this, by the way, the line looks bigger. Do you see it? Yes? And now I want to plot at each step that I add another polynomial, the function total, okay? But I don't want to erase whatever I've plotted before, so I type in hold on. Okay, hold on to that plot. I'm giving you some more plots, right? So now I take this line, I copy it and paste it over here, and over here I write total. Okay. Are you with me? So if I run this, I will get many curves, but I don't understand what they mean, right? So first of all, I don't like that these numbers are so small. So what I can do is set GCA. I still don't know what it means, but it works. Okay. Do you see? Now, it would be awesome if I could write some text here. For example, like n equal, at least writing like 0, 1, 2, 3, 4, 5. That's probably the case, right? And the exponential function. How do you write texts inside plots? Legend is one way of it. Yes, very good way of it. But I will use this one. So let me just put it over here. It says text, and it says x end. What it mean x end? It gives you, if I run just that one, it gives you 3, which is the value of x at the end of the vector. Okay. Okay, I should erase Sine and put it exponential. So basically, if I run these lines, it will give me an exponential function, and it will write down exp here. Okay. Why at this particular point? Because I told it to write it on the end of x and the end of total over here, right? So if I take this line and put it over here, then I still keep x end. I put here total end, the end of the total function, and I need a number written as a text, right? What do I use? Num to string, number to string function, and I put n here. Okay. So if I run it, you can see that as this goes up, 0, 1, 2, 3, 4, 5, the function approaches the exponential function. Do you see it? I want to show you one more thing, which is I will just erase this repetitive thing here. I will put it down here, and I will increase it to 15, for example, and run it. So this one shows you the what happens after 15, after you include 15 terms. The two curves are indistinguishable, right? They are on top of each other. Let's do it for 7, and maybe there is tiny bit of deviation over here, right? But as you keep putting terms, it will approach the exponential. Okay. By the way, actually in principle it needs to work close by 0, okay? But exponential function is a special case in which like putting the more terms you put around x equals 0, the better it gets everywhere, okay? It works everywhere in exponential function. Let's look at the sine function. Okay, where is it? The sine function has this kind of expansion. Do you want me to derive it? No, you don't want me to derive it. Well, basically, you can think of it, this is Maclaurin series again of sine function, and you can imagine sine, derivative of sine is cosine, derivative of cosine is sine. So whenever you have sine, you will get 0. So it will be starting as x plus x cubed over something, etc. Right? So let's do it for sine, and you will see that it's kind of different. It's complicated. Maybe I should write here sine. And maybe just the end product. You can see that it explodes if I add more regions. So let's go back and make it 7 and 7 and 7, 7. So this is the sine function, and this is the approximation that you get with 6 elements. Okay? Still with me? It will be more and more clear why I touched this subject in the next lectures. So please don't question too much. And I'm actually coming to this point. Have you seen this beautiful formula before? Euler's formula, yes. Is there anyone who hasn't? You haven't, right? I want to derive it for you. You need to see this at least once in your lifetime. So basically, e to the x is 1 plus, I already forgot, x plus x squared over 2 factorial. Etc., right? What is sine x? It's x minus x cubed over 3 factorial plus x to the 5 over 5 factorial, etc. Do you agree so far? Yes? What about cosine x? 1 minus x squared over 2 factorial plus, I believe, x to the 4 factorial minus, etc. Right? How can we put these equations together? You can see that the exponential has this minus, plus, 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 while sines have minus, plus, minus, this should be minus. Again, minus, plus, minus, right? Well, you can use are you sure about this one?
If you write cosine I e to the ix.
Yes.
I will
Exactly.
minus.
Exactly. E to the ix will give me 1, right? Then plus I times x, right? And then minus x squared over 2 factorial. Are you with me? Yes? Then what's the next term? Minus ix cubed over 3 factorial. And it goes on like this. So if you rearrange these things, then you can see that it's basically 1 minus x squared over 2 factorial plus etc. plus I times x minus x cubed 3 factorial etc. Right? What was this? Cosine x, right? Plus I times sine x. You see? And of course it yields the famous mathematical constant reunion, e to the I pi equals minus 1, right? Who is seeing this for the first time, right? This is for you guys. Okay. What is the next subject? The next subject is we are moving more towards the art of computing, so-called, right? So, have you heard of Newton-Raphson method?
Yes.
Thank you. What is it used for?
In order to estimate the value of a function numerically.
Numerically estimate the value of function. Is that accurate?
The solution.
The solution of the function, yes. It's helpful to find the root, right? And basically, this is another thing that I stole from Wikipedia. Let's start from the beginning. x1, you take tangent, you go back x2. As you can see, this procedure takes you to the root of the function, the place where it cuts x equals 0. Do you see why? If everybody sees why, I can continue. If you don't, please let me know. Let's see this animation let's look at it for a while. So you start with x1, you find the tangent, and basically you go down until you hit this point, right? And you keep continuing. And if you are already close to the root, then it is guaranteed that you get the root. Okay? Now, we will come back to this, but let me ask you some questions. What is the solution of this one? And please don't laugh. X equals 1, right? What is the solution of this one?
Plus minus 1.
Very good. Thank you very much. So x equals 1, x equals minus 1. What is the solution of this one? So it has to have 3 roots, right? X equals 1.
Minus 1 is
It's tricky, right? We don't know the other 2 solutions. But we will come back to this. Let's take, maybe the answer is hiding over here. what is the solution of this one? We can basically take from here that it can be separated into x squared equals 1 and x squared equals minus 1, right? And this one yields x equals 1, x equals minus 1, and this one gives you what? X equals I and x equals minus I, right? Are you happy? So, if we draw this so-called unit circle in complex plane, okay, real, imaginary. Anyways, generic. You can see that x, the first equation, the solution was this one, right? For the second one, the solution was this one. And for the fourth one, the solutions were this one, this one, this one, and this one. This is 1, this is I, this is minus I, and this is minus 1. Now tell me, what happens with x cubed minus 1? One root is over here, right? The other ones are actually over here and over here, right? I hope this is something new that you learned in this, today, right? For some of you, of course. So x equals 1 is one solution. What is this one? So it's 90 degrees here, 30 degrees here, right? So this one is minus 1 over 2 plus square root 3 over 2i. Oh, physics habits. Sorry. And this one is x minus 1 over 2 minus square root 3 over 2i. Okay? Now, I want to go back to Newton-Raphson and actually write a code that finds the roots of x cubed minus 1. Okay. So let's look at it again. If you have a function that is to be solved, then you basically get your first iteration, then you take minus fx divided by the derivative of fx, right? So let's start with x equals 2, okay? And for n equals 1 to 10, let's make 10 iterations. Maybe let's call this one x1, and the second iteration will be, no, let's go from 1 to 10 and write down xn plus 1 is equal to xn minus that function, right? Cubed minus 1. Are you with me? Yes? Divided by 3 times xn squared. Okay, let's run this. So I don't like it this way. So let me put it like this. Okay. So it approaches 1 quite quickly, right? Yes? Good. I can see that many of you are bored. Sorry about that. But at least I have one eye candy for you today to show. And I'm about to reveal it. So the question is, the following. So we have ourselves this complex plane, right? And we know that this is one root, this is another one, and this is the third one, okay? So my question is, I just started from 2, right? I just started from here and went to this root. Which one would take me to this root? And which one would take me to this root? Okay, do you understand the question? No? Okay, let's, I just said x equals 2, right, in this program. X equals 2, and it took me to x equals 1. What if I start with x equals I? Okay, 1i. Okay, where does it take me? It takes me to this minus 1 over 2 plus square root 3 over 2 root. So I started from here and I went over here. Do you agree?
Can you start from minus 1?
Minus 1. Yes. You wanted to experience. Yes, I can. I probably it will go to 1. Okay, that's my guess. Yes, it goes to 1.
So it does not converge to the closest one always.
Yes, yes, it does not converge to the closest one. So far our experiments shown that this goes over here, right? And this one goes over here. This one goes over here. What if we look at all possibilities? Okay. Actually, your example ruins the surprise, but because I was going to say that, is it something like this, like you mentioned, the closest one? So if it was the closest one, then this region should all move to the blue one, right? This region should all go to the yellow one, green one, and this one to the red one. Clearly, it's not the case, right? So let's start by defining these regions. Okay, how can you express these regions in MATLAB? Again, to remind you what this course was all about, it was all about coding, right? Learning new tricks, etc. And I know that it looks like we are playing a game, but there is always some deep message here, okay? And I hope you will receive it in a moment. Okay. So, for example, a new trick that we will learn here. Let me clear it out. And so I start with clear and I write this line. Okay, what it means. It's very important for the future courses. So I draw a mesh grid between -2 and 2 for x and y. After I run this, what happens is that x gets the values that are changing as the columns change, okay? Like -2, -1 over 199, -198. And y gets the values that are changing as the rows change. So basically it's like n by n matrix, and x, both of them has n by n. X gives you the position of x coordinate, the value of x coordinate, and y gives you the value of y coordinate. Are you still with me? Yes? Good. So now you can do this, something like this, okay? You can write down z equals x plus 1i times y. So all the y components will be multiplied by I. So you will get yourself the value of complex number at each coordinate. Do you agree? Yes? Good. Do you have a question? I will write one more line and let's see what happens. I'm basically cheating from here. So what it does is quite complicated actually. It takes the mode with respect to 2 pi, and before that, the main thing here is angle z. What it means? It gives you the angle of the complex number. So if it's, for example, 1, then the angle is 1. What if it is 1 plus I? Yes, 45 degrees. 1 plus I is something like something that is over here, right? So this angle gives you 45 degrees, right? So, of course, this is given in radians, so we need to, you know how to turn it into, yes, 45 degrees, right? Okay, never mind what this one is, the rest one is doing, but what happens is that it basically draws these regions, okay? This one is where the x equals 1 solution is sitting, this is the other solution, and this is the other solution, okay? What I will do is I will keep applying Newton-Raphson method, okay? And I will look for the angle as I apply. So you can see I did it over here. And we are about to finish the lecture, so that's why I'm moving quick. So as this one progresses, you can see that we are doing this Newton-Raphson method over here to all individual points. So that's what happens at the end of the day. There you go, the eye candy. Maybe we can make it even slower if we take this. So now you are seeing it in more high definition and much slower. So basically these are the regions, the basin of attraction for the roots as you apply Newton-Raphson method. Okay, so all of the blue ones, as you suggested, the minus 1 over here goes to here. Okay, the yellow ones, for example, you start from here, you are much closer to this root, but you go up here, okay? We will come back to these plots and everything in the next lectures.